SwayamPrabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibration, continuing our discussion on the forced vibration response. In this lecture, we will focus on the excitation that comes from the base. So, when the ground excitation is the excitation for the vibratory system, how the response is obtained. Now, we train our attention to another very interesting response phenomena. Till now what we have done is, suppose this is our vibratory system, then we said that okay, this entire chassis of the the vehicle is like a mass, and we modeled the suspension using this spring dashboard system, and maybe this engine is creating excitation force. Engine has crankshaft and the IC engine is spinning with some speed, and that is going to create excitation source for the chassis to vibrate. Okay. So, it is like a mass sitting on some suspension on the spring dashboard system, and then if we quantify and characterize this inertia property, the stiffness property of the suspension, the damping property, and we know at what speed the crankshaft is rotating and what is the unbalance or residual unbalance in the crankshaft, and primary and secondary and so on. So, we basically characterize the excitation force also. Now, if that happens, then what is the ensuing vibration response which is felt by the rider? That is what we have done in the past. Okay. All the time this was modeled like a simplified single degree of freedom vibratory system. Okay. Now, what we are going to look at is, supposing we ignore the excitation source from the engine or from any other excitation source on the mass. Okay. We only say that this vehicle is cruising without vibration on a level road, and then it suddenly goes through a wavy road. Okay. So, the road profile here is making this kind of a motion. I mean the profile is such that it is not a straight level road. If that happens, then what is the similar vibration response the chassis is going to generate? Okay. This is called as base excitation, excitation coming from the base. Okay. For a compressor or a huge air conditioning unit, the excitation can come from the ground and it will excite that whole system. Okay. If you have a heavy forging hammer nearby, that forging hammer is going to generate excitation coming from the ground, and your other sensitive equipment or machinery can get excitation from the ground. That force gets somehow get transformed into the motion of the base. Excitation due to earthquake is nothing but a base excitation to the building structure. So, then what is the method, what is the way we should model this system for such kind of excitation coming from base? That is what is the job. So, now you can, as we can take this particular example, that you have a bike which is having its static deflection may be given by this value, the road profile. Now, road profile, although it looks a little arbitrary here, but for the sake of understanding basics of response to base excitation, we assume this road profile to be modeled like a sine wave. Okay. So, we are approximating this profile as a harmonic profile of certain amplitude. So, I can assume some amplitude here, capital A, and some wavelength here. Okay. And so, with some amplitude and the wavelength, that gets characterized, the road profile is characterized as a sine wave. So, the question here that is being posed is at what speed the biker should not move or cruise his bike to avoid resonant vibrations. Okay. It is possible to discuss, I mean possible to realize that there would be a speed at which the rider will experience large resonant vibrations, okay, and we shall discuss mathematically how that turns out to be. So, the question is to determine the speed at which the bike should not be run to avoid resonant vibrations, and this is of course the first part of the question. The second part of the question is that if we assume the damping to be 0.05, which typically is a low level of damping we expect in the suspensions, then what will be the vibratory amplitude if the cruising speed of the bike is, let us say, 75 kmph, right. So, he is moving with 75 kmph, what will be the vibratory amplitude? All these questions are required to be addressed now. Now, we do not have now an expression that defines this vibratory motion. If we say that this vibratory motion will be same as your static deflection divided by square root of 1 minus r square whole square plus 2 zeta r whole square, will that be correct? That is not true, because we have defined all of that with the assumption that this is subjected to harmonic excitation force. Here that is not the case. So, we will have to first figure out what is the expression that gives me the amplitude of vibration which is being asked in this particular case. Okay. So, let us get back to our normal usual vibration analysis process. What it says is, this physical system you convert it into a simplified vibratory model. Now, we assume that this wavelength is large enough compared to the distance between these two wheels. So, we model this entire system as a simple single degree of freedom system with a single mass, single stiffness and a single damping. So, this is how I will model this system as this, which itself can be further simplified by a simple single spring, single mass and single dashpot vibratory system. Now, this response which we are trying to figure out y as a function of time t will obviously be in response to the motion x as a function of time. Okay. So, as this vehicle moves over this profile, the tire is going to be perturbed or moved up and down because of the profile of the road. Okay. This is like an excitation to this vibratory system coming from the base, that is why it is the base excitation. So, it is going to be like this or more precisely like this. Now, if that is the case, tell me now how do you formulate the governing equations. So, very simple, this is y and this is actually x. So, if you go back to your basic vibratory system process, I mean basic vibration analysis process, the first step is already done, getting a simplified vibratory model and defining the degrees of freedom, the motion. The motion involved here is basically y of t, it is the response of the chassis. Will you call this as a degree of freedom? The system is this, no? This is external, this is out of the system, and I will discuss that part again in more detail later, right. So, at the moment just assume that it is the y of t which is the degree of freedom, the vertical motion of the chassis or the mass involved. Okay. Xt is impressed external perturbation to the system. Okay. We will come back to that point. Now, the simplified vibratory model is built. What is the next step? Vibration analysis process. Step number 2, get the governing equation of motion. What do you do for getting the governing equation of motion? Either use energy method or use Newtonian approach. So, you have a mass here which has y, y dot and y double dot. What is the force which is going to act here? Suppose that there is a motion of the mass in the vertical direction, that is the positive direction here. The spring and the dashpot will provide the forces. So, if you isolate this mass free body from the surrounding acts, the forces due to the spring and dashpot will act on this mass, right. What will be the value of the restoring force? Will it be k into y? What is the restoring force? It is the stiffness constant or a spring rate, in this case for a spring rate times the stretch in the spring. What is the stretch in the spring? It is not y, the stretch in the spring is going to be the net stretch. So, that is going to be k into y minus x, because the other end of the spring is being moved, right. We are assuming that the tire is not going to lose its contact with the road profile. So, the tire follows the profile of the road, which means that the other end of the spring is going to move with a value equal to x of t at all times, okay, while the mass and therefore, the other end of the spring is tracing out a path which is given by y of t. So, the net stretch in the spring is going to be y minus x, and therefore, the restoring force is going to be k into y minus x.
What about static deflection?
We are ignoring, because we have discussed all that once the mass is put on the spring and it deforms, your y of t is actually being defined with respect to the already deflected position, static deflected position, right. So, static deflection, mg and all that will not come into picture here as well. Okay. Now, after this, what is the dissipating force? Similarly, there is no need for a further explanation here, that also will follow the same process. Now, you apply to get the governing equation once the free body diagram is made up. M, now will it be m y double dot minus x double dot here? Will it be m y double dot minus x double dot? So, it is the absolute y double dot that we take, right. So, the inertia is going to be proportional to its global acceleration value, right, y double dot. It has nothing to do with what x double dot is. So, m y double dot is equal to summation of all the forces, and that would be what? Minus, because this force is opposite to the direction of the acceleration, assumed acceleration, minus k into y minus x minus c y dot minus x dot. And so, if I reorganize this equation, let me reorganize this expression. Now, what I have is m y double dot plus c y dot plus k into y equal to, so I have taken all y terms on the left hand side, is equal to c x dot plus k x, right. Now, why have I left x terms on the right side while bringing all y terms on the left? Generally, what we do? What do we do? the excitation to the system which is external to the system is typically kept it on the right hand side, and all your your inertia, damping and the restoring forces, they are internal. I mean they are generated because of the vibratory motion, the motion of the system kept on the left hand side, right. Now, on what basis are these sort of an external force? Now, again let me go back to our rotor vibration problem. Was this excitation force whose amplitude was m epsilon omega square, did it ever depend on the vibration amplitude r? It was a fixed value changing with only time. Okay. It does not depend whether the rotor whirls with r equal to 0, r equal to 1 or r equal, even when r equal to 0 it will have the same value. So, whether the r is 0, 1, 20, 30, 100, the excitation force is independent of the way the system responds or the way system vibrates. So, the forces which are independent of the vibratory motion are external, it only depends on time. Now, this x of t, this is your x of t, will it change its profile depending upon how the chassis vibrate, right. That x of t is completely defined, let us say by sin omega et. Its amplitude is all defined based on how much is the the profile here, which is completely defined here like this. So, x of t, actually x of t will be a function of cruising speed of the vehicle. Okay. This excitation frequency omega e is a function of the cruising speed. We will define that and discuss that also later. But the point is that x dot and x which we have taken on the right or kept on the right hand side is kept because it is external to our vibratory system. It has nothing to do with the way the system vibrates or responds, and therefore, that is on the right hand side. That is an external excitation to the system. Is that clear? Okay. Now, having got this governing equation of motion, what do you do with it? That is our step number 2 completed, step number 3 completed. The last step is to the last but one step is to get the solution. Again, as I said, once you get the governing equation, getting the solution is straightforward, okay, for a vibratory system, particularly linear vibratory system. What is our excitation? Now, this x, have we defined this x of t? Yes, it is. So, capital X, in this case this A is nothing but I can say that this A is nothing but capital X. It becomes easier, and the format remains familiar as the textbooks. So, we say that this x has an amplitude capital X e to the power j omega t. This is the way x of t is defined. So, when the vehicle moves, it experiences maximum amplitude, minimum amplitude, maximum amplitude harmonically. This is how it happens. The tire will be moved up and down harmonically with this profile. So, this is our assumed input, just like we defined f of t as f naught e to the power j omega t. The way we defined as an external excitation force, this is an external displacement excitation to the system, base excitation. Now, if the excitation is harmonic, we have been saying all the time for linear system, the response will also be harmonic with the same frequency. So, now y of t can be y e to the power j omega t. Now, what you do, the way we have been saying, you know, y double dot y, x dot x, they are all defined through these. Okay. So, you can substitute the derivatives into this equation, and what do you finally get? You get capital Y separating out capital Y from the left hand side and taking the capital X from the right hand side, you will get an expression. Okay. This process we have done many times, so I will not repeat that. It is a small exercise for you to figure out yourself, and then it is possible to show, if I define the excitation to be a harmonic excitation x e to the power j omega t, the ratio of the output response, that is capital Y here, and referred to or normalized with respect to the excitation amplitude at the base. So, what we are saying is, how much is this Y amplitude related to the excitation, base excitation amplitude capital X. That ratio is possible to show that it is given by this expression. Okay. In fact, when we wrote Cx dot plus Kx on the right hand side of the governing equation, you may say that the excitation force is nothing but K plus J C omega x e to the power j omega t. That means, it is nothing but a force excitation with a force magnitude given by this. Okay. If you substitute for x dot and x, that is basically is what you will get as a excitation force. So, that way one can interpret it, but this is what you have, the ratio of the output response of the chassis of the vehicle normalized with respect to the input motion at the base, that ratio is given by this expression, simply put. And it is possible to show that the angle or the phase between the response y and response and the input x is given by this expression. So, you can find out the phase by using this expression. Okay. So, those things I am leaving it to you to derive it yourself, because the process has been discussed many times over. Okay. How does it look like? If you plot it, it looks like this: y over x, the response amplitude looks something like that. Okay. Slightly different than capital X over x s t, there is slight difference here, and that difference is very important from the point of view of vibration isolation and vibration control. So, what you see again is that as the damping increases, the peak response at the resonance keeps on reducing. So, damping is quite useful and valuable. The phase looks like this, it is slightly different than what it was in the earlier cases, but still, you know, in general they are roughly in phase, and they get out of phase post critical operation speed. Okay. So, something, I mean, these graphs are quite self explanatory in terms of its inference. However, the most important difference here is the way these graphs look below this point and beyond that point, and that is very important to understand. Now, what does this y over x represent? It says that how much is y for every unit amplitude of the base motion. That means, if the base motion is 1 unit amplitude, how much will be y relative to that. Okay. The value of 2 or 4 or 6, what does they represent? What does it represent? This number, that number, for example, if the value of y by x is this, it says that if the base motion or the profile at the base has 1 unit amplitude, the chassis is going to vibrate 6 times the base input amplitude. what do you get? You get amplified response. Would you like you to ride on such a bicycle or a bike where slight perturbation on the road gets amplified and you keep on moving up and down? You do not, right? So, this range of operation, right from right from speed ratio 0 up to this point, there is one very important difference or very important commonality here, is that till you operate up to this point, irrespective of the damping, at all the speeds you will get some amplification, which means that your response is going to be always more than the input excitation. Clear? What happens beyond this? That ratio drops below 1. Okay? That response drops below 1, which means that when you operate at speeds more than this value, okay, it is not the speed, it is the speed ratio. So, you will have to multiply it with omega n, but then when you operate in this range, the response keep on getting attenuated. That means, you keep on reducing the response. For every unit amplitude, there is a fraction response. Okay. If the x, capital X is 1 unit, you will get fraction of 1, right. So, maybe 0.2, 0.1, 0.05 and so on. So, it pays off, right. So, it makes sense to operate somehow beyond this particular value, and that happens irrespective of the damping value. So, it is a universal point actually, damping does not change that position, all curves pass through that point, right. But can you make out some problem in this range beyond 1.4? Maybe look at this point. Yes, you do get some attenuation. So, the amplitude just of course decrease, but then you wanted, I mean, when you want to reach to this point, you do pass through this resonance anyways, right. So, as you keep on increasing your cruising speed, you will eventually end up crossing the resonance. What do you expect and what do you want at the resonance? The damping to be higher value. Okay. So, let us say if I do not want the rider to get large amplitudes, maybe I will choose zeta equal to 0.2 or so, or maybe 0.3 or so. So, I will definitely get double the amplitude at resonance. Look at what happens in the post 1.4 value. If I do not have damping, that means, or have a very reasonably small level of damping, this light blue color curve shows that I get a fantastic attenuation, much lower vibration response, right. But if I have a large level of damping, even 0.6 or 0.3, they are going to generate a much higher vibratory response. Now, it does not show up in the linear plot because the dampings are so closely, and then there is a huge difference between 1 and 0.1, right. So, 10 times drop, but they will all they will not show up. So, we will have another slide in which I show this in a dB plot or a logarithmic plot. There you will find a huge difference in the way the damping plays its roles. Okay. So, if you want to attenuate and control your vibration level, the best way is to attain that is to operate in the range which is beyond this, and typically there is no hard figure here, but in practice people prefer to keep it at least 3 times the natural frequency, which means that the excitation frequency should be typically greater than 3 times the natural frequency. So, this frequency ratio R omega over omega n should be typically 3. I mean, it is not a sacrosanct figure as such, you can also have it 2.5, whatever is reasonable possible. Because even if you, I mean, even if it mathematically says it is advisable to be larger the better, but you do not really gain too much of advantage by just keep on increasing. There are other practical problems which we will discuss shortly. But now what you are observing here is that the damping is not something which you should always keep on increasing just because you are going to get a quieter vibrations or a less level of vibrations at resonance. You cannot simply arbitrarily keep increasing the damping the way you want, right, because you are going to cross through this resonance within a very short period of time. You are not going to linger around the resonance region, right. So, the passage through the resonance is quick usually, and then you do not really mind for a very short period slightly higher vibration, provided in lieu of that, if you keep on operating for a long periods at your operating speed, maybe somewhere here for a long period of time, you expect lower amplitude to be more beneficial, and there the lower level of damping will pay off. I mean, lower level of damping will always be beneficial. So, this is an important aspect of base excited response that you should be mindful of. This particular critical point below which the amplitudes are larger than the base amplitude and beyond which the amplitudes of vibrations are attenuated, that R value is 1.4, which also you can theoretically estimate from the expressions that we have seen in the previous slide. Okay, so, this is very important. Okay, it actually is square root of 2. Yes. What is omega for us? Omega n of course is the natural frequency for these systems, right, but then what is omega in this case? That is what we are going to look at in the problem that we wanted to solve. So, the same problem that it is following a sinusoidal path, and the amplitude of that waveform is 8 centimeters, and the wavelength of that waveform, the profile of the road is 15 meters. So, first objective is to find the critical speed, right. Now, going back to the previous graph, what is the value of this omega? Okay. What is the value of this omega that gives you the largest amplification of the base motion? Okay. Most of the times we do not complicate things, we say that okay, it is undamped natural frequency. With some amount of damping, it will be moving little bit here and there, but then it is going to be quite close to 1. Right? So, for all practical purposes, it is fine to calculate this omega based on the undamped natural frequency. So, now if we want to know what is the speed at which the vehicle should not be run, so that there is large amplification, is by finding out what is the undamped natural frequency, and then to answer your question what is omega in this case, we will discuss. The static deflection of the automobile is 10 centimeter. Can we get from this the value of omega n? You all know that, yeah. So, the static deflection, what is static deflection? Yeah. The weight divided by the stiffness of the suspension, that will give you the static deflection, will it not? So, so that basically gives me the ratio k over m, which is nothing but static deflection divided by g. And so, because I know that for a simple single degree of freedom system, the natural frequency is obtained like this. So, I will simply replace k over m by the static deflection divided by g. Now, that static deflection is your delta, which is given here. So, omega n is going to be square root of, you be mindful of the units here, and that, yes. Oh, I am sorry, I am sorry, I am sorry, I am so sorry about it. Yeah, G by delta. Okay. Okay. So, that is G over delta, and that is G over delta, and then you have 9.81 over 0.1, and you calculate, that turns out to be 9.9 radians per second. Okay. Now, what would be the critical speed? How does mathematically it is going to be 9.9, but how does it translate to the cruising speed? Because the vehicle, I mean, ultimately you have to talk in terms of the cruising speed of the vehicle, right. Now, if the vehicle completes this waveform at a speed of v, okay, we know the relationship, right, of the frequency, the speed and the wavelength, right? That is going to be v over f clearly, is not it. So, the wavelength is lambda. If this wavelength is, and f is the frequency in terms of cycles per second, and the v will be appropriately having its own unit. So, f into lambda is going to be v. Now, you need to be careful about choosing appropriate units for this. Okay. So, suppose f turns out to be like, so if you have this lambda as a wavelength which is given as 15 meters, okay, and multiplied by f is equal to the cruising speed. Now, this cruising speed is what we want to find out, right. Now, if you substitute this frequency, okay, in terms of cycles, in terms of radians per second, and that would come from this, by assuming that this critical frequency is going to be similar to your, or it is going to correspond to the natural frequency of the system. Okay. So, you basically have time that it will take for you to traverse this distance, right. So, how much will be the time traversed, time required to traverse 15 meters, if your cruising speed is v meters per second supposing. So, then what will be the time period? Yeah, your lambda divided by your cruising speed. Now, this lambda is what? 15 meters of wavelength, cruising speed is assumed let us say v meters per second. Okay. So, that is your time period, and now the frequency, if I want to know in cycles per second, it will be 2 pi 1 by capital T. So, if you want to convert this into the radians per second, this is going to be 2 pi by T. So, this is going to be 2 pi over 15 into V. Now, this frequency, which is now being written in terms of in the units of radians per second, that can be directly related to the critical frequency or natural frequency. So, 9.9 would be equated to 2 pi V over 15, and therefore, the critical cruising speed in meters per second would turn out to be 15 into 9.9 divided by 2 pi. Okay. So, roughly 150 divided by 6.28, yeah. So, 25 times 3.6, that would give you this value, because 3.6 is for converting this 25, approximately 25. I am just making a small mind calculation, which is going to be 25 point something or whatever meters per second. So, this is all going to be in meters per second, converted into kmph, you need to multiply it with 3.5, 3.6, right. Okay. So, that those calculations you can do, which will give you the critical cruising speed. So, if I run this vehicle at a speed of 84.74 kilometer per hour, okay, then there will be maximum amplification of this 8 centimeter profile. Okay. So, that basically becomes my critical cruising speed at which I should not run the system. And are you clear now what is omega in this case? That omega is going to come from your lambda and of course, your cruising speed, the cruising speed V. Okay. So, if you have a very low cruising speed, this motion is going to be followed at a very low frequency, and if you track or traverse that profile very fast, then your the wheel is going to move back and forth very fast. Okay. That is how omega is indirectly linked to the wavelength and the cruising speed V. Okay. Now, the last part is how do I find the amplitude of vibration at 75 kmph. Now, I can also get this 75 kmph converted into omega. How do I do that? Omega will be 2 pi over capital T, that capital T is going to be 15 by 75 converted into meter per second, that is going to be this, will it not? That is the denominator. Okay. So, what this actually is 2 pi over f, which is going to be lambda over v. Okay. So, cruising speed 75 kmph divided by 3.6 will give you meter per second, and that 2 pi by capital T is going to be my omega at 75 kmph. Now, that I can get and it turns out that it is 8.72 radians per second. Clear? If I substitute now how do I get the amplification or y by x ratio? By using this expression which we have seen earlier. What is the value of zeta to be used in this expression? I can use that 0.05. What is r? Omega over omega n. What is the omega n? In my case it is 9.9, and omega for 75 kmph is 8.72 divided by 9.9, right, that is r. So, in this expression of y over x, I have got everything that I need to solve it for y by x, and when I do that, okay. So, here r is 0.88, this value is 0.88, which means that I am operating somewhere here, right, below critical, which means that I expect amplification, right. And what will be the value of that amplification? For a damping ratio of 0.05, I am basically somewhere here also, roughly there. It is difficult to see from that graph, but when I actually calculate it, it turns out that this amplitude is 33.906 centimeters. Now, what was our capital X? It is this 8 centimeter amplitude is getting amplified to 33.9, which is slightly more than 4 times amplified. So, that is 4 times amplification of the base motion. Okay. What do you do? So, again this entire vibration process that we learned in last couple of slides, starting from your physical bike system converted into a simplified vibratory model, deriving the appropriate governing equations, assuming solution, solving it, getting this kind of an expression, and then you substitute and solve it. What you have got is the value of y. Now, you interpret it your interpretation is that the speed at which you are operating is incorrect. But suppose I cannot go beyond that, my speed limit restricts me to run it at only 75 kmph. What do you do? Would you allow yourself to be oscillated with that amplitude? What options do you have as a design engineers? Is there any way in which the advantages that we discussed of operating here, okay, which means that your frequency ratio should be greater than square root of 2 or 1.4. What is that? Now, we just say that I cannot operate with a speed more than 75 kmph, but I can always tinker with this denominator. What is that denominator? Can I change the mass of my bike? By the way, what do you expect this value, this ratio to be? Greater than, let us say 3 or maybe close to 3, let us say, to start with, means that it should be greater than square root of 2, 1.44. So, to get that, and I cannot change the numerator, what should I do to have a higher value of R? Is to reduce the value of omega n, right. What is reducing omega n mean? Increasing the mass. Now, increasing the mass has its own problems. Increasing mass means you get a pillion rider, right. So, you are going alone and I cannot change the mass of the bike. So, one possible option is to redesign, and this is the most common and most practically viable option compared to increasing or changing mass. And so, what we are looking at here is that I would like to redesign my isolation system to change the omega n value. Okay. So, I am basically going to change the value of omega n, and I am going to change this to, let us say, 2.75 radians per second. I think that is the value it is. So, that 2.72 or so. So, that the ratio turns out to be now 3.2. So, I reduce the natural frequency from 9.9 radians per second to 2.72 radians per second, and then that gives me a higher value of R. So, my R is now going to change from 0.88 to 3.2. So, I am going to now operate at the same cruising speed. I am going to work at this particular R value. If I use this R value keeping the damping coefficient same, so I am not changing the damping properties, with that I get the value of response y equal to 0.13. 260 times reduction with respect to what I was getting when I was operating pre-critical range or less than square root of 2 value. That is the advantage here. Okay. And so, this is how the interpretation and making it work, like you redesign the system so that the vibration response is better. Okay. Now, role of damping here, I must not increase the damping here. I will quickly go through the resonance point, and lower damping will help me here. You just redo this exercise by adding or increasing the damping ratio from 0.05 to, let us say, 0.3 or 2. You will find that you will not get so much of reduction. Okay, so, in terms of transmission of the effect of vibration of any dynamic system, we had already discussed how the base excitation to the vibratory system gets transmitted to the inertial mass, and then if the transmissibility is more, then unit amplitude of base excitation gets amplified to a multi times increase in the base amplitude of the vibratory system. Okay. So, the mass vibrates with amplitude larger than the base amplitude, right. That is what we have seen, that the vehicle, if it is passing over a wavy road, then the amplitude of that excitation, which is basically the amplitude of the base motion, that amplitude, if the vehicle is moving at a very slow speed, the mass will undergo an amplitude that will match with the profile of the base, right, or the road profile. But if this speed increases, this amplitude itself is going to be much larger, right, than the amplitude of the base excitation. So, if this is x, the amplitude y with which this inertial mass vibrates, that amplitude y will be many times more than the input amplitude x. That is what the base or the displacement transmissibility that we have seen. Okay. So, that was discussed as the displacement transmissibility. And that was defined as output displacement amplitude versus or divided by the input displacement amplitude. Okay. Displacement in the sense the base excitation amplitude. So, it actually refers to the same way, you know, we defined dynamic magnifier or magnification factor, which is basically how the output gets amplified for the given input, right. In this case the input is x, how it gets amplified to a larger value of y, that is what the displacement transmissibility is. Now, what we discussed obviously is that if we have the speed omega greater than square root of 2 or 1.44 times the natural frequency of the system, then this ratio actually reduces or drops below 1, okay, which means that when you are operating with a frequency which is larger than square root of 2 times the natural frequency, then there is no amplification. In fact, the amplitude y actually drops compared to the base input amplitude, that is x. So, that displacement transmissibility becomes less than 1, and that is what is desired, you know, you for every input amplitude your response should be less than that, that is the effective isolation, right. So, what we discussed is that in the case of a vehicle moving over a wavy road, whenever we ensure that this frequency omega is greater than omega n times square root of 2, then the amplitude of output response is less than that of the input response. In fact, if we it is observed that if this ratio omega over omega n, that is r, is greater than 3, the amplitude is a fraction of the input amplitude. Okay. That is what we have discussed already. So, what the focus of attention for us with that example was actually displacement transmissibility, and we are going to now look at force transmissibility, that means how the force gets transmitted to the ground. Okay. It is quite similar as such to whatever we have discussed. Let us look at this. So, the example that has been shown here is an equipment. You are quite familiar with this equipment. What is that? It is an outdoor unit of a split air conditioner, right? You see this quite often in all households, and this condenser unit is mounted typically on some frame, but here for the sake of illustration it is shown for a heavy kind of a condenser unit. It would be isolated from the ground or from the civil structure through an isolator. As you can see, this is the isolator which is used to isolate the condenser unit from the structural the civil structural base. Now, this isolator is flexible in the sense that you can always model this isolator like a spring dashpot system, the way we usually model the mounting of any equipment, right. So, the mass is sitting on top of this mount. So, the mount is actually modeled in a simplified fashion as a pair of stiffness and damper. Okay. You can quantify the values of this K and C by actual testing, and we have discussed that how the testing is done. Typically put it on a force displacement, I mean the machine which measures the force and simultaneous displacement, and using that you can actually plot the force versus deformation or stress versus strain, and then you will get a hysteretic loop like this. And then using that you can find out what is K and what is C. K will be basically the slope of this loop, and then C is something which you can obtain from the area below this within this curve, which is going to be the dissipation energy. So, essentially giving you an equivalent viscous damping coefficient. It's actually there is no viscous damping here, it is all structural damping, but for the sake of using it in the equations that we have already derived, it is quite common to numerically find this equivalent damping coefficient by using or measuring the area which below within this curve, which denotes the energy dissipated, and that we have had enough detailed discussion of how equivalent viscous damping coefficient value is obtained. Okay. So, with that, coming back to what we started discussing here is, if this kind of a machinery is mounted on these isolators, we can model this entire vibratory system like a mass and a spring dashpot system, the way we usually do. K and C now in this case will be equivalent of all the 4 supports as a simplified model, and single degree of freedom x of t is assumed here again. And what is there inside this condenser unit? Maybe an electric motor which will be rotating with certain speed, and may be connected to a blower here which is going to rotate this blower at certain speed. So, not only although you usually have maybe a single rotating shaft, but it is quite common that a complex mechanical system may have multiple shafts. Okay. So, you can imagine that there could be 2 excitation force, one due to the unbalance in this pulley of the electric motor, and in addition to that maybe this fan will have certain unbalance, right. So, you may have a situation here that you can have some amount of excitation force in the mass itself. So, what I am representing here is the excitation due to the rotating shaft or a rotating unbalance mass. So, that rotating unbalance is going to generate an excitation force to this inertial this system, and we can actually write this as F naught sin omega t or F naught cos omega t as the excitation force to this mass, and in the response to this kind of an excitation there will be some dynamic response of this mass. Okay. So, what is going to happen, that there is going to be a steady state vibratory amplitude which is going to set up a harmonic excitation force. Excitation force is going to create a harmonic response x of t. What would it do? You may notice that because this mass is connected to the foundation, which maybe you can take this as a parapet wall of a building. Now, you have seen how these condenser are mounted. So, ultimately what is going to happen is that this vibratory motion of this mass is going to create a stretch in the spring and some dissipating force generated in the dashpot. Now, although there is no formal dashpot here, but we have seen how this type of structural damping is modeled like a spring with a complex stiffness, that we already know. But the point is, the moment for the sake of simplification, just treat this as a spring dashpot system. So, whenever there is a motion here of the mass, there would be a stretch in the spring and a dissipating force in the dashpot generated. What will happen, because of this stretch, not only there is a restoring force which will be created by the spring on this mass, but there would be similarly a pulling force which will be created on this base, isn't it? And similarly, there will be some force which is also going to get generated at the contact point of the dashpot. So, basically, because of this kind of a harmonic motion of the mass, through these connecting elements which we have seen here, through these connecting elements there would be a force which is going to get transmitted in the structure on which it is mounted. It is quite obvious, right. So, now the source excitation force is this F naught, and because of that source excitation force, the vibratory system vibrates, and that creates a transmitted force getting into the ground or foundation. Okay. Now, what would happen because of this? This force is also going to be a dynamic force, right, because this force itself is sort of a dynamic force which is source acting to excite the system to vibrate. Now, this transmitted force is going to create a problem. For example, if this is a part of a building, now whenever there is excitation force which is transmitted to this structure, that is going to all shake the whole structure. So, no matter how strong these walls are, there will be some response to such kind of a dynamic force which is acting, and that would create this building internal walls are going to vibrate, and that is going to radiate sound inside the building. Not only the structure itself will completely vibrate, but will also create rumbling sound inside the building, okay, within the walls of the room. So, all of that is discomforting, and therefore, there is always a need to ensure that for a quieter workplace, quieter homes, you need to somehow get all these forces transmitted to the base as little as possible. So, what should be so most of the times these condenser units are all properly designed, they are supposed to carry out their intended function. So, finally the engineers are left to somehow figure out what should be the characteristic of these isolation mounts, so that the transmitted force is as low as possible given the excitation force F naught which is generated. Okay. So, it has to operate at a particular speed, it has been already balanced to the extent possible. So, because of its own action, you cannot avoid some force being generated at the source. The only thing that you can do is now to somehow design this isolation, okay, meaning design this particular mount, okay, to have certain stiffness, certain damping, so that the transmitted force is minimum, so that the vibration and the sound generated, okay, is minimum. So, coming back, what does this mean? This transmitted force to the source, this is quite similar to y upon x that we have already discussed as a displacement transmissibility. The output displacement to the input excitation motion, the amplitude of those waveforms, base motion amplitude, that ratio should be as low as possible. Okay. On similar lines, this ratio which is called as transmissibility or force transmissibility, that should be as low as possible. So, that FTR is for a given value of F naught, FTR, the transmitted force is as low as possible. So, the whole thing here therefore, means that we should understand force transmissibility the way we understood the displacement transmissibility, right. What do you do now? Suppose we are required to analyze this, what happens afterwards may not be our concern at the moment. We all know that what will happen if this FTR is large. So, our focus would be on this system, okay, so that FTR is small enough. So, this is the summary of this lecture. So, we had a small example of a vehicle traversing on a wavy road profile, and in that context we explored the role of damping, the role of excitation frequency, and how by an appropriate choice of the suspension parameters the response amplitude of the chassis can be reduced significantly. In that context we discussed the displacement transmissibility. In fact, the response of the chassis to the base excitation amplitude is what we call as the displacement transmissibility. So, these are a couple of questions, simple short questions that you can now answer.